we're doing project 1 with the buck converter with a fixed voltage, and we're group 3. I'm Chu.
I'm DJ.
My name's Aaron.
I'm Elir.
And this is our prototype of our buck converter. And this is the microprocessor board we use to drive the pulse width modulation for the switch. For our project, we were to design a buck converter. We were supposed to take 12 volts DC and drop it down to 9 volts across the load. We used the standard topology Dr. Ko gave to us in class, but we implemented some additional features such as a microcontroller to control the pulse width modulation into an optocoupler for system protection to drive the gate driver to operate the switch. The specifications we needed for this project were to have an efficiency greater than 60%. We have to have an output power up to 4.5 watts and an output ripple of less than 2%. We did this by increasing the size of the capacitor to reduce the ripple. Our ripple turned out to be less than 1%, significantly less than 1%. Our load, we could achieve the 4.5 watts across it. We did that with an 18 ohm resistor. We tested it that way, which we'll show you in a little bit. And our efficiency, we calculated the input current, input voltage, output current, output voltage, and that ratio gave us an efficiency of roughly 75%. In order to achieve these specifications, we needed to operate the microcontroller at a specific frequency and duty cycle. The specs for our microcontroller, we chose 30 kilohertz due to 2 reasons. It was above the audible range, and 30 kilohertz because we did not implement closed loop control. 30 kilohertz allowed, when we attached the load to it, the voltage didn't sag as much. We needed to create a duty cycle of 25% into the optocoupler, since that inverted the signal. That gave us this 75% duty cycle driving the gate. Here's an image of the waveforms. So channel 1 is our input from the microcontroller. It's a 30 kilohertz square wave with a duty cycle of 25%. Channel 2 is the outside of the optocoupler. Right here I'm showing that there's a 2 millisecond delay. This was one of the problems when using the microcontroller. We could not decrease the duty cycle too much more than this because of the delay time. From this graph you can see the specs here. We did achieve the 30 kilohertz, and then this would be your 25% on time, your 75% off time, and then as you can see the optocoupler has the opposite of that. That's what's actually driving the transistor.
Alright, this is our setup for our buck converter. Right here we've got our microcontroller from microprocessors course. And here we have our buck converter here. Right here is our input square wave to our circuit from the microprocessor into our optocoupler right here. And then this is our high side gate driver. Right here we're measuring the output from the optocoupler that's actually controlling our transistor. Alright, now we're going to show you guys the functionality of our buck converter. Right now we have an input of 11.98 volts, and on our output, since our output's in parallel with our input, we get just about the same thing. And then when we apply PWM to our circuit, the transistor is going to conduct a little bit, and we're measuring our output, so it's going to sag. We're going to have some slight losses across our capacitor, inductor, and transistor just due to the leakage current. And then when we apply our load, this is the load that's going to deliver the maximum power consumption, 4.5 watts. And as you can see here, our output voltage is 6.82 volts. It sags because we have a lot more current being drawn through the circuit, and those losses are reflected in our voltage output. And then once we pull the load out, our circuit settles down to our designed 9 volts.
We want to make sure that our circuit can drive a real load, so we attach a 12-volt DC fan in it. Even though it's only outputting around 7 volts, it will still be able to drive a 12-volt DC fan. And without the load, the voltage will go back to our output voltage of 9.22.
We would like to show that our circuit meets the efficiency specifications above 60%. So we are going to measure the voltage and the current of the input. We have a voltage of 11.95 volts and a current going through our circuit that is 0.35 amps. Now we're going to show you the voltage across our load and the current that will go through our load. So we have a 6.72 volts and a current of 0.48 amps going through our load. Here we have our voltage input and output measurements, and also our current input and output measurements. So we can show you that our circuit has an efficiency that is above 60%. Actually, our circuit works a little bit even better, so we have an efficiency of 77.12%.